Hi, today we're going to solve some puzzles. In a few seconds I'll put 3 puzzles up on the screen, and that's your chance to pause the video and have a go at solving them for yourself. Or you don't have to do that, you can just sit back, relax, listen to my explanations, and maybe you'll learn a thing or two. Problem 1. If the knots where multiple ropes meet are too thick to cut through, what is the least number of cuts that must be made in order to completely cut through this rope ladder? The options are 4, 5, 6, or 7. Problem 2. What is the minimum number of edges that must be removed from this network graph in order to isolate x from y so that there's no path along the edges between them? The options are 4, 5, 6, or 7. Problem 3. If a tan snowflake has area T and a dark green snowflake has area G, what is T over G? The options are 2, 3, 4, or 5. These puzzles are all daily problems from Brilliant.org. This video is sponsored by Brilliant, and I like working with them because it enables me to share problems with you guys and to make videos that I wouldn't otherwise be able to. So let's have a look at solving our first problem. In this picture here we have a fence that is very similar to the problem that we're solving, but it's not exactly the same. We're just going to use it to illustrate in general how you solve problems like this. Our fence is a network of ropes, and networks sort of exist all over the place, and they could carry anything. In this case, our network of ropes is carrying tension between the 2 fence posts. So our goal here was to cut the ropes so that the left and right post are completely separated. For this little example here, you can actually do it with 5 cuts. And you might be able to find that just maybe by looking at it and a bit of trial and error. But really we want to know if 5 really is the optimal answer, and we need to sort of prove that you can't do it in 4 or fewer cuts. That's where something called the max flow min cut duality comes into play. Understanding the max flow perspective here means that if we were treating our network like a system of pipes carrying water, what is the maximum flow of water from the left to the right side of the system? We find this by drawing in as many horizontal paths as we can find across the network. These paths can't reuse any of the same bits of rope, but they can reuse intersections. In our little example here, in green, you can see you can draw in 5 distinct horizontal paths across the network. Because it is possible to draw in these 5 distinct horizontal lines, we can conclude that 5 cuts is not just sufficient, but also necessary in order to completely sever the fence. In order to sever the fence, we have to cut across at least one segment in each of these green paths. So the max flow diagram of 5 distinct horizontal green lines serves as a bit of a visual proof that the fence cannot be severed in 4 or fewer cuts, because it would necessarily leave one of these independent paths uncut. This idea works both ways. If you know that you can sever the fence in 5 cuts, then that serves as a proof that the maximum number of independent paths across it horizontally is also 5. This maximum flow minimum cut idea is useful for us, but it's also very useful in computer science, a place where you'll see a lot of networks for things like carrying data and information. So network reliability, availability, and connectivity questions are all related to each other and to this max flow min cut. For example, this website says that airlines can use this principle to decide when to allow planes to leave airports to maximize the flow of flights. So the flow in our network can really refer to anything. There is some more information on Brilliant about this, including a mathematical look at the proof, but for now, let's solve the exact problem that we were given. We'll mark in our maximum flow paths across the network. It's 1, 2, 3, and 4. None of these ropes here will work because we can't reuse any ropes. So we know that we can complete this complete cut in 4. Let's find our 4 cuts. We could do 1, 2, 3, and 4, which gives us our solution. Problem 2 is actually very similar, so we can solve it now. Instead of going from left to right on a ladder, we're just going from one node to another. We can still find our maximum flow by connecting these nodes in as many ways as possible. I've managed to find 5 distinct ways to connect these points, so we should be able to completely sever them using 5 cuts. If we look at it, we could pick 1, 2, 3, 4, and 5, which gives us our solution. Our last problem is about the Koch Snowflake. I don't know about the pronunciation, but these are an example of a fractal. So you start with an equilateral triangle, and then you add an equilateral triangle onto each edge, and you continue to grow out like that until, we can't really resolve what's going on the screen. It's an infinitely repeating pattern, and it's a pretty interesting one that often people like to play around with, sort of generating little bits of code which can make these snowflakes, and it's sort of a nice look into the world of fractals. So if we look at how its perimeter is changing for each generation, we can see, we add this equilateral triangle onto each edge, and the length, the perimeter of the shape changes by a factor of 4/3 each time, it looks like. And it's going to keep going like that forever. So the perimeter of this shape is actually infinite. However, its area is not infinite. So if you see in this picture, you can draw a circle around the area, and that sort of allows you to think about the fact that this isn't going to be expanding out an infinite area like its perimeter is getting infinite. In our problem, we were asked to compare the areas of 2 of these snowflakes, and we just have to be glad that we're not being asked to compare the perimeters, because that might be a bit trickier. We can start by drawing in our original 6 pointed stars into 2 of the snowflakes. If we zoom in on this section right here, we see that one of the sides of our big triangle is the same as the height of 2 of our smaller triangles from our smaller snowflake. So if these are all set to a side length of 1, and we know that they're equilateral triangles, so that's 60 degrees in there, a little bit of trigonometry can find the height of these triangles and tells us that the side length of our big triangle is square root of 3. These snowflakes are similar shapes, so everything's the same. One is just a little bit more zoomed in. Something to know about similar shapes is that the ratio of areas of similar shapes is the square of the ratio of corresponding sides. So if we know that the sides correspond as 1 for the smaller triangle and root 3 for the larger triangle, then the ratio of the areas will be 1 to 3. You could see this fact in something like a square. If its side lengths were all x, then its area would be x squared. For example, a circle, if its radius was r, then part of its area would be r squared. So if G is our smaller circle, T is our bigger one, then T over G is going to be equal to 3, and that's our answer. If you want to have a go at some more of these daily problems, you can go to brilliant.org/Tibees and sign up for free, and the first 200 people to do so can get 20% off an annual premium subscription. So thanks to Brilliant, and thank you for watching.